Hi class, welcome to the next section, chapter 1.4. Today we're really going to focus on rate of change. So we'll talk about this in terms of lines, right, slope, and in general for curves, for functions. Okay, so rate of change is something that's very important in calculus. We're going to study that a lot in this class. It's actually kind of the main focus of what we are studying for this course. Okay, so this will be our first discussion on rate of change, and we'll talk about it several times after this as well. So for a line, that's the easiest time to really talk about rate of change, right? We know this as the slope of a line. It's the rate at which something is either increasing or decreasing, right? So we're going to use this idea of increase and decrease for a rate of change to talk about pretty much all functions, right? It's the ratio for our vertical change over the horizontal change. So how much am I changing up and down as I move forward or as I move back? But typically we talk about moving in a forward direction, right? As I'm progressing forward in time or distance, how is my output changing, right? So if we kind of just start off with the standard way that we talk about slope, which is looking at 2 points that lie on a line. We'll call the first point x0, y0, and the second point x1, y1. Yeah, I don't know why these are squares here instead of circles, but it's fine. So we like to talk about the horizontal change and the vertical change, right? So this creates a right triangle for us, where the length of this triangle is the horizontal change, and the height of this triangle is the vertical change. So the difference, the length here, is the distance from this point to this point, so x1 minus x0, and same thing here, the height here is y1 minus y0. Okay, so that's our vertical distance and our horizontal distance. So our slope, which we call m when we're talking about lines, right, y equals mx plus b, is the same as, a lot of you have heard this as rise over run. Okay, so you know, previously I just talked about it's our up and down over our left and right movement. An easier way to talk about this is the change in my y values, the change in my output, over the change in my input values, or the change in my left and right movement. When we talk about change in mathematics, we use the Greek letter delta, okay, this triangle. As we move up in calculus, specifically in calculus 3, this triangle starts to mean different things, but for right now we represent it as change. Okay, and so the change in y, or delta y, is y1 minus y0, as we saw before in the graph. And the change in x is delta x, which is x1 minus x0. So you'll see this delta y and delta x notation a lot throughout your calculus sequence. Okay, so if our slope is negative, that means that we are decreasing as we move forward in time, right? So this is a downward slope. If I had a little guy on here, as I progress to the right, they would slide down this hill, right? That's a negative slope. This is a positive slope because if we move to the right, we would be going uphill. This is no slope because there is no change in height as I move in either direction, left or right. And this is undefined because there is no left or right movement, right? Denominator of 0, but there is up and down. So we really don't know how to quantify this in numbers as movement, right? Which is another reason why we don't divide by 0. So an undefined slope just means I have a vertical line. Okay. So using our function notation for my point, x0, y0, we would call this as x0 and x0 being plugged into our function f. Okay. And a second point would be x1 and f of x1. Right? So if I plug this into my notation for slope, right, for m, which is y1 minus y0 over x1 minus x0, instead of y1 and y0, I would use the function notation. So f of x1, right, for y1, and f of x0 for my y0. So this becomes my slope when I'm dealing with a function. So remember that a function is not always linear. Right? A function is generally a curve. So this allows us to find the rate of change on average from one point to another. Okay? So this average rate of change is the slope of what's called the secant line. A secant line is a line that intersects a curve at 2 points. It can intersect at more than 2 points, but we generally take it from one point to the next point of interest, right? So it's 2 lines passing through a curve. So when I look at it in this way, here I have a curve, a function. I can't see what's going on past this point or past this point. Maybe it does all kinds of stuff, or maybe it's just a quadratic function. It doesn't really matter because it's not a line. So I'm really interested in what's going on from one point, which is x naught, f of x naught, me plugging this point into my function, and some other point, okay? And then me connecting those 2 points with a line is a secant line. And the slope of this line is the average rate of change for my function from this point to this point in time. Okay. So average rate of change is f of x1, right? Your larger point generally, minus f of your smaller point over x1 minus x0, the things that you plugged in to your function at that time, right? So if we look at just the top portion, this f of x1 minus f of x naught, that is what we call the net change. Okay, the net change is just basically, from this point to this point, what are my difference? What's the difference in output? How much have I changed, right? So I've gone up this much over this distance, right? So just the difference in height is what's called the net change. When we divide that by that distance, then it turns into the average rate of change, right? So the net change is just numerator for the average rate of change. So let's go ahead and do an example. So we'll go ahead and do a word problem. I'm not going to talk too much about how to approach word problems. This is something that you guys should have plenty familiarity with at this point now. But I will say that generally my word of advice for word problems is to read it a few times. I generally will read a word problem maybe about 4 times. The first time I'll read it and I won't do anything but try to understand what's happening, try to absorb some information. Second time I read it, I will write some things down, right? X is this, Y is that, what have you. Really what I try to do first is draw a picture, okay? And then on the third time I read it, I'll try to start to label things. And then if I need to read it a 4th time, then I'll use that to put some relationships together, form some equations, some equalities, that kind of stuff, right? So for this example, let's say that a rock is being thrown from a 100-foot cliff, okay? The person who throws the rock is 6 feet tall, right? So they're on top of a cliff. So we have 100 feet and 6 feet. The rock is going to reach a max height of 30 feet above the cliff when it is 20 feet from its release point, right? Its initial point of its trajectory, right? It's going to land in the water that is below the cliff that's 70 feet from where it's thrown. We want to find the average change in the height of the rock, so average rate of change, from 10 feet from where it was released to 50 feet from where it was released, right? So, so that's one time reading through it, right? So next time I read through it, I'll want to try to draw something. So I know that I'm going to have a 100-foot cliff. So let's kind of go start with that. Let's try to draw a picture. I always draw pictures. It helps us out. So I have a cliff, right? I know there's water below, and I know that there's a person on top of the cliff. The height of this cliff is 100 feet. This guy or girl here is 60 feet. Okay, so I have that. I know that trajectory is a parabola, so I can draw this flight path, right? I know the initial point that is released, right? So initial point means that time is 0, or a distance of 0, right, in this case. I know when it hits the water, it says that it's at 70 feet away, okay? And I know its maximum. Its maximum is 30 feet above the cliff, and that happens 20 feet from the person, okay? So I have my trajectory. I have 1 point, 106, at a distance of 0, because that's when it first gets released. I know when it hits the water, 70 feet away, and it has a height of 0. Okay. Anything below this tends to be negative now, right? We're under sea level. In this case, we're calling this our our zero, our ground, right? I know the maximum value is 30 feet above the cliff, not the person. So this is not 136. It is 100 feet and another 30, right? So again, we always want to make sure we're reading carefully. A height of 30 feet above the cliff, and that's 20 feet away. So I got my initial value, my terminal value, and my max value. Okay, 20, 130. The two last pieces of information that we have are them asking us what's happening 10 feet away and 50 feet away, and then finding the average height of that, or the average rate of change, which we know will be the slope of the secant line that connects those 2 points. So very, very similar to what we just did here. Okay, so we have all this. I'm interested in what's happening at 10 feet away. I don't know what that height value is. And 50 feet away, I also don't know what that height value is. So I need to know these output values in order to find the slope of the secant line. Before I can find the slope of the secant line, however, before I can find these outputs, I need the function. So that's kind of the order that I need to go. Find the equation that models this curve. Then I can plug in 10 and 50 to get their outputs. And then I can find the rate of change by using that slope formula for the line that connects those 2 points. Okay, so this is what I want. I want the slope of this line here. So we have some missing values. We need to create a model. I know that this is a 0 of 70. I have a point here, so I could kind of put this into vertex form, right? Looking at the shifts, I know I have a horizontal shift of 20, a vertical shift of 130. I know that the parabola is negative, so I could put all of that together. For quadratics, I think something slightly easier is to put it into a factor form. All right, it really doesn't matter. There's lots of ways to do these things. Hopefully you have a nice set of tools in your tool belt for dealing with quadratics at this point, right? So I know that the line of symmetry is in the middle for a quadratic, right? So 20 is the halfway point between whatever, if I were to continue this here, this intercept and this intercept. So I'm doing it in a slightly different way rather than using the vertex form, just to give us some variation in our approaches, right? Half the distance from one end to the other is then going to be 50, right? So x value of 20, I have a 0 at 70, that's 50 away. That means my other 0 is 50 in this direction, okay? So that means that my other 0 would be at negative 30. So if I kind of extend my parabola to model the entire thing with the invisible part that is not applicable to our situation, I could find the model very easily using the x-intercepts, right? I have an x-intercept at 70 and at negative 30, so this is what the factor looks like. I don't know if this is stretched in some way, so I have to keep that constant in front of a, right? So really what I need to do is I need to just use one of the points that I know, okay? 70 and 0 is not going to work, because if I make this 0, then everything is 0. So I would use the 20 and 130, output of 130, input of 20 in each piece, and I would solve for a here, right? So this is what my extended graph looks like. As you see, I got a different style of dotted line here because this dotted portion is not applicable to the application of this system that we're dealing with, right? So let's plug in some values. If I can, I plug in 0 and 106 here. That is actually easier. So I have 30 times negative 70 times a is 106. Okay, solve for a. So you don't always have to do the math. You can kind of just manipulate stuff and do the math at the end. That's something you'll see quite a bit in this class. So when we simplify this down, we get 53 over 105. So that is my value of a. So that means that my parabola has this equation in its factored form, right? This is how I could factor it. Again, if I want to put it into vertex form, it would be negative 53 over 105 times x minus 20 squared plus 130. This value of a never changes, right? No matter what form we're in, standard form, vertex form, factored form. It's all going to be the same, right? Same value of a, that is. So let's see here. So our missing points are at x equals 10 and x equals 50. The nice thing about factored form is it's easy to plug stuff into here, right? So first I'll plug in 10, and then I'll plug in 50, and then I can get my output. So I can start to find my average rate of change now that I have a function. So plugging in 10 will give me a 40 and a negative 60. Okay. Simplify those out, and I get 8480 over 7. Again, one thing to note, if I haven't said it so far in this class, is I do not like decimal approximations, right? In this class, exact values whenever possible. Yeah, this is an ugly fraction, but using the decimal representation means that you have to cut off some information somewhere, which means you lose accuracy. So if I do ever allow decimals, or it's the only way to like approach a problem, I generally say keep 4 decimal points of accuracy. But generally you want to use exact values whenever possible, and you don't cut off or round anything until your final answer. Okay. Otherwise you get a rounding error, which can become a huge problem, especially later on in later math classes. We actually have some sections here in this course where if you're rounding things, you're going to have a bad time, and you're definitely going to get the wrong answer. So make sure you're using exact values. Okay, it's a good habit to pick up right now, especially if you're going to be an engineer or a physicist. Okay, so again, leading into the next one, I want to plug in 50. I'm just going to do the same thing. So I'll get 80 and negative 20. Simplify this out, and I get 16960 over 21. Okay, so my average rate of change is in this exact value minus this exact value. Again, if I did not use exact values, I would have some decimal error happening here, especially since I would be dividing some decimal values. Okay, it will not work out very well. So here I'm going to make a common denominator, so I just multiply this top and bottom by 3, as you see here. Combine my like terms, and now I can divide this numerator basically by 40. Okay, so I'm start to simplify things. So this actually comes out rather nicely, not super nice, but it's not too bad, right? If I want to from here, I would now plug this, I would now give a decimal approximation form if that was my choice, or if I say, you know, hey, keep this to 4 decimals of accuracy, you would do it exactly to this point, and then you would say, well, this is equal to 9 point something something something.